My name is Sukhada Fadnavis. In this talk, I will introduce my paper titled A Note on the Shameful Conjecture. The following are the prerequisites for understanding this introduction: familiarity with basic graph theory, basic graph coloring, and probability theory. If you are unfamiliar with these topics, reading the following Wikipedia pages should enable you to follow this introduction. We begin with the setup. Consider a finite simple graph G. For example, G could be the 3 path. Now let's consider a 3 coloring of G. Let's say we have 3 colors: green, red, and blue. Now one possible 3 coloring of the graph is as follows. Say vertex 1 is colored red, vertex 2 is also colored red, and vertex 3 is colored green. Another possible coloring would be as follows. Say vertex 1 is colored blue, vertex 2 is colored red, and vertex 3 is colored green. Note that even though both of these are 3 colorings of the graph, the first coloring is not a proper coloring of the graph. Recall that a proper coloring of a graph is a coloring of the vertices so that no 2 adjacent vertices have the same color. The main goal of this paper is to understand the probability that a uniformly chosen random Q coloring of a graph G is proper. Here Q is the number of colors available. Let's consider an example. Once again, consider the graph G, which is a path on 3 nodes. In this case, there are 27 possible 3 colorings of the graph G as listed here. Out of these 27 colorings, there are 12 highlighted colorings, which are the proper colorings of this graph. Hence, the probability that a uniformly random 3 coloring of this graph is proper is 12 over 27. In fact, it is easy to see that for this graph, P sub G of Q equals Q times Q minus 1 squared over Q cubed. Because Q times Q minus 1 squared is the number of proper Q colorings of this graph, and Q cubed is the total number of possible Q colorings of the graph. Note that this probability increases as a function of Q. In general, we are interested in answering the following question. Is the probability P sub G of Q an increasing function of Q? Intuitively, one would think that this is true. The reasoning being as follows. If we have more colors to color the vertices, then the chance that 2 adjacent vertices have the same color should fall. What may come as surprise is that this statement is not always true. The following is a counterexample due to Colin McDiarmid. Consider the equipartition complete bipartite graph K and N on 2n nodes. On the right here, we have an example of a K33. There are 2 to the 2n total possible 2 colorings of this graph. Suppose the colors are red and blue. The proper colorings of this graph consist of one side getting red colors and the other side getting blue colors, and there are two ways to make these choices. Hence, P sub G of 2 equals 2 over 2 to the power 2n. Now we consider the proper 3 colorings of the graph. Suppose we have the colors red, blue, and green. In this case, there are 6 ways to proper color this graph using exactly 2 colors. For example, we could choose the 2 colors red and blue, and then color one side with red and the other side with blue, and so on. And there are 6 times 2 to the n minus 2 ways to proper color this graph using exactly 3 colors. So first, we pair up the colors so that 2 colors are used to color one side and the remaining color is used to color the other side. That gives us that p sub g over 3 equals 6 plus 6 times 2 to the n minus 2 over 3 to the power 2n. It is easy to see that for large n, the left hand side is greater than the right hand side. Thus we see that the intuitive idea that p sub g of q plus 1 should be greater than p sub g of q is not necessarily always true. Bartels and Welch conjectured that this inequality should hold true for large values of q, in particular that p sub g of n is greater than or equal to p sub g of n minus 1, where n is the number of vertices of the graph. This conjecture was dubbed as the shameful conjecture. The conjecture was proved by Fengbing Dong in 1998. He proved that p sub g of q plus 1 is greater than or equal to p sub g of q for all q greater than or equal to n minus 1. In this paper, we prove the following complementary result. Let delta be the maximum degree of g. Then the above inequality holds true for all q greater than or equal to 36 times delta to the power 3 over 2. The proof of this result relies greatly on the method used by Alan Sokal to bound the roots of the chromatic polynomial of a graph. To read more about this, please take a look at the paper. The link to the paper is provided below. Thank you.